So, welcome to another Sussex Universe talk. My name is Dr Stephen Wilkins and I'm a reader in astronomy at the University of Sussex. Today I'm going to talk about the origin of the elements. So this is where the elements which make up the periodic table come from. I realised after I proposed this title that it was actually a little bit dry, and so maybe it's better to say something like, actually, where did all the gold come from? Because ultimately that's what we're going to lead towards in this talk. Before I do this though, a little bit about myself. I was born in Yorkshire. I was then an undergraduate student in physics and astronomy at the University of Durham, after which I went to the University of Cambridge to do my PhD, and after that I spent 3.5 years as a researcher at the University of Oxford. Then almost 7 years ago now, I became a lecturer and then senior lecturer and most recently reader in astronomy at the University of Sussex. I'm currently also the Director of Outreach and Public Engagement and an STFC Public Engagement Fellow. My research actually focuses not on the chemical elements, or at least not directly, but it actually focuses on the first stars and galaxies to form in the universe. The early universe is accessible to us because of the finite speed of light, so when we look back, we look out into the universe, and we're actually looking back in time. Much of my current work is actually preparation for the upcoming Webb telescope. This is a flagship astronomical observatory built by NASA, the European Space Agency, and the Canadian Space Agency, and it should be launched sometime next year in 2021. But this talk is quite different. So the brief for this talk was that last year, 2019, was the 150th anniversary of the periodic table. The formulation of the periodic table was a really important milestone in understanding both the properties of the elements themselves, but then ultimately atoms. And so in this talk, which is really split into 3 parts, I'm going to start by giving a brief overview of the structure of atoms and how atoms can be rearranged to form new elements. I'll describe the observed abundances of elements in the solar system, the Earth's crust, and even the human body. I'll then describe the various astrophysical processes which are responsible for producing the elements. Okay, so first of all, we're going to talk about how atoms are rearranged and what atoms are. Okay, so every atom is composed of a nucleus that contains 1 or more protons and a similar number of neutrons, although not exactly the same number. Collectively, we call these nucleons, and they actually contain the vast majority of an atom's mass, about 99.9%. Atoms also do have electrons bound to the nucleus, so they're typically on the outside of an atom, whereas the nucleus is on the inside. And obviously, being composed of protons and neutrons, the nucleus is positively charged, whereas the outskirts of the atom are negatively charged. Put together, most atoms become neutral. These two positive and negative charges cancel out, although that's not always the case. Any 2 atoms with identical numbers of protons in their nuclei actually belong to the same chemical element. Atoms with the same number of protons but different amounts of neutrons, however, are called isotopes. The common isotopes of hydrogen and helium, for example, are hydrogen-1, this is just standard hydrogen, deuterium, sometimes known as heavy hydrogen, and then tritium, which actually has 2 neutrons and a proton. Now the interesting thing about tritium is that it's actually radioactive. It's unstable and it will decay. Similarly for helium, we have helium-3 and helium-4. Isotopes crucially have very similar chemical and molecular properties, but crucially they have different masses and stabilities. Now, atoms can be rearranged through several processes. Although we like to think of atoms as being unmovable or unchangeable, this isn't really true. And in fact, it's only by rearranging atoms that we're actually able to make the entire spectrum of the periodic table. So first of all, possibly the most important mechanism is nuclear fusion. So this is the reaction where 2 or more nuclei combine to form 1 or more different nuclei in subatomic particles. Now, to actually fuse an atom together, we need to overcome the repulsive electrostatic force between the 2 nuclei. These 2 nuclei are positively charged, so they want to repel each other. In order to make them fuse, we require very, very high temperatures. And so what you're seeing here is the fusion of tritium and deuterium coming together. And in this case, the fusion of tritium and deuterium comes together to form helium-4, a leftover free proton, and energy. Nuclei can also capture neutrons, so this is a different way in which nuclei can grow. This is really important in nuclear reactions, but as we'll see, it's also crucial to explain much of the periodic table. So in this example, silver-109 actually captures a neutron and becomes silver-110. Okay? Now the silver-110 here is actually radioactive again, and we'll come back to why that's important later. Atoms can also disintegrate or decay, and there are several different types of decay, although the most prominent are alpha decay, where you lose an alpha particle or a helium-4 nucleus; beta decay, where you essentially change a proton or a neutron into a neutron or a proton; and then spontaneous fission, where a larger nucleus can break apart into two roughly equal-sized pieces. Okay, so that was our introduction to how we rearrange atoms. What I'm now going to talk about is the abundance of elements in the universe, the Earth's crust, but also human bodies. Okay, so if we look at the abundances of the elements in the universe, well actually in this case the solar system, because universe really depends on when you look. If I look really far away, I'm looking back in time, and so I'm seeing the universe before it's maybe had chance to build up lots of heavy elements. Okay, so I'm going to use the solar system as my definition of the universe here. And if we try and express the fraction of mass in each element on a simple pie chart like this, we see it's kind of boring. So we see that actually most of the mass in the solar system is in hydrogen, around 75 or 76%. Then around another 20 or 25% is in helium, and only a few percent, maybe 2%, is in elements heavier than hydrogen and helium. Okay, so actually all the things that we're maybe really interested in, the oxygen, the iron, the nitrogen, carbon, gold, are all contained in this one little slice down here. So this diagram isn't particularly useful for explaining what is in the solar system or the abundances of different elements. So instead of using this, I'm going to show you a slightly different diagram. So what I'm going to do is I'm going to denote the abundance by a colour on a logarithmic scale. What this allows us to do is compare very large and very small abundances. So if you look at the scale on the right hand side, each increment you're changing the abundance by a factor of 100. Okay, so the very yellow colours over here have an abundance of close to 1. Okay, so things like hydrogen, which make up most of the solar system, that's going to be close to 1. Okay, but things that are very rare, like gold, are all the way down here in the blues, where we see lots and lots of zeros after the decimal point. And this just tells us that gold, for example, is very, very rare. So what I'm going to do now is take this colour scale and colour my entire periodic table using this scheme. So this is what happens when we do this. And again, you can see what we saw before with the pie chart. The hydrogen and the helium, they're very abundant. They make up most of the mass of the solar system. But then we see more detail now. We see things like carbon, nitrogen, oxygen, neon, iron. They have high abundance, not high compared to hydrogen and helium, but much higher than, say, things like gold and silver. Okay, so you can see here that the blues are very, very low abundance. So, okay, so starting with things like beryllium, going down to gold, silver, etc. We can see there's some interesting trends in here. Generally, the more massive the element, so going down the periodic table, the rarer or less abundant it becomes. Okay, but there are some exceptions to this rule. For example, lithium, beryllium and boron are actually much rarer than carbon, nitrogen, oxygen, despite being simpler atoms. So this diagram is really, really important because this is what we need to explain. With all of our different processes that we'll talk about later, ultimately we're going to try and explain this entire diagram, why there is so much hydrogen and helium, and why there is so little gold. Okay? But also more generally, where does the gold come from in the first place? Now we can also look elsewhere in the universe, perhaps specifically at the Earth's crust. Okay, so this is just one example of the Earth's crust over here. I believe this is a diamond mine in Canada or Siberia. And if we look at the pie chart for the Earth's crust now, we see something slightly different. So we see that gone is the hydrogen and helium, but in is oxygen and silicon, which together form most of the rocks. And then we see lots of aluminium, iron, magnesium, sodium, and calcium. Okay, but again, many of the elements that we may be interested in actually all the way containing this little sliver over here. So this is where all the gold and platinum are. So even in the Earth's crust, this kind of pie chart diagram really doesn't convey all the information that we care about. So again, we can look back at our periodic table. And we now see this is quite different from the periodic table coloured by abundance for the entire solar system. So gone is hydrogen and helium being the most abundant. Now we have the oxygen and silicon and iron, magnesium, etc. much more abundant. In fact, it's interesting now that helium, the second most abundant element in the universe, is now actually rarer than silver on the Earth's surface. just to point out that down here is where gold is. One of the reasons why I keep going on about gold is because gold is actually crucial to my day job. So most of my work at the moment, or at least my research, focuses on preparation for the James Webb Space Telescope. This is one of the mirror segments of Webb, and the reason why this looks gold is because it actually is gold, or at least it's coated in a very thin layer of gold. The reason for this is that the Webb telescope is designed to operate in the infrared, and actually gold has much better reflectivity in the infrared than, say, aluminium, which most traditional mirrors are made out of. Okay, so this is one of the reasons why I care about gold. Okay, we can also look at humans and see if they're different. Again, we see a slight change from the surface of the Earth now. So oxygen is even more important, but we see that hydrogen has become more important again. Okay, this is not really a surprise given that hydrogen is a component of water and carbohydrates and even proteins, what we're basically made of. Okay, we also see carbon, nitrogen, calcium and phosphorus are all very important as well. But we can return to our periodic table and look at it in more detail. And again, we see a different pattern of abundances now. Actually, this is a little bit misleading because not all of these elements here actually have a biological role in our bodies. Many of them just accumulate because they exist in the environment. If we concentrate on the ones that actually just play a biological role, these goes down to like this. Okay. But what's really interesting here is that there are actually some relatively rare elements, for example, chromium and molybdenum, which actually do play an important biological role. Okay? So these are the things that make up us, or which are vital for our functioning. And it's actually a surprisingly large number of the elements on the periodic table. Okay. So what I'm going to do now is talk about the origin. So this is the main part of the talk. I'll talk about the astrophysical processes responsible for the formation of all of the elements. Okay, so what I'm going to try and do is explain this periodic table. This was the periodic table for the entire solar system. Okay. Now, in addition to using abundance or using colour for abundance, I'm going to use the opacity, okay, to denote the fraction that we've accounted for so far. So what I'm going to do is talk about a whole range of different mechanisms, and some mechanisms might only account for, say, 50% of a particular element, in which case you're going to see that we're going to denote that element on the periodic table by this kind of intermediate faded colour. Okay, but we'll see this we'll see this clearly in a second when I actually show you some examples. Okay, so let's go all the way back to the beginning. Now, if we go all the way back to the Big Bang, for around the first 10 seconds of the universe's history, the universe was so hot that atomic nuclei couldn't form without almost immediately being broken apart. But as the universe expanded, it cooled. And eventually nuclei could form without being immediately broken apart. Okay, so we had a range of nuclear reactions which took place after the first 10 seconds of the universe's history. So for example, protons and neutrons were able to combine to form deuterium, deuterium combined with deuterium to form helium, and so on. Over the next 20 minutes or so, almost all of the neutrons that were present in the universe are turned into helium-4. Now, because there were far fewer neutrons than protons present, not all of the protons went to form helium-4. Instead, many of those remain as hydrogen-1. So we have a situation like this on the left-hand side at the beginning. We see a small number of neutrons in the purple and a larger number of protons in the blue. Around 20 minutes later, after Big Bang nucleosynthesis, we see that all the neutrons get locked up into helium-4. Okay, we can see these two atoms, whereas the remaining protons just remain as hydrogen-1. Now, it turns out helium-4 is a bottleneck. If you want to fuse beyond helium-4, the problem is that there are actually no stable atoms with either 5 or 8 nucleons. So you can't take helium-4 and glue on an extra proton, that's unstable, and you can't take helium-4 and glue on another helium-4, that's unstable. Okay? So in the very early universe, the density or temperature is never high enough to actually allow us to form any significant amount of heavier elements. We do form small amounts of lithium and beryllium, but very, very small amounts compared to what is formed later. Okay, so if we look at our periodic table now, and we can now colour code both using the abundance in the universe, but also now the fraction that we've actually accounted for so far. So what you can see is that Big Bang nucleosynthesis accounts for virtually all of the hydrogen and the helium in the universe. That's why these are very bright, vivid colours, but only a small amount of the lithium, which itself is very rare. So what else is there? Well, as the universe expanded, eventually clouds of gas, the hydrogen and helium that were formed in the Big Bang, they could collapse to form objects like this. So this here is one of my favourite images from the Hubble Space Telescope. This is the Pillars of Creation. And what we're seeing here are huge clouds of gas and dust which are actively being turned into stars. So to cut a long story short, because this isn't a talk about star formation, what we know is that clouds of gas collapse under their gravity to form cores of objects when nuclear fusion is able to occur. Now, when the core of this cloud of gas gets hot enough, it's able to create energy via nuclear fusion, which stops the subsequent collapse of the object, thus producing a star. And so when we see this happen in nature, we see things like this. So this is the result of the collapse of a very large cloud of gas, forming many thousands of individual stars here. Now, for most of a star's lifetime, it fuses hydrogen, left over from the Big Bang, to produce helium and energy. And it's that energy which stops the star from collapsing under its gravity. And so over a star's lifetime, it's able to convert all of its protons into helium, energy, and a smattering of other subatomic particles, including neutrinos and positrons. Eventually, though, the star will run out of core hydrogen. Fusing helium is tricky for two reasons. First of all, helium nuclei really don't like being very close together. That means you need to get your star very, very hot before helium will fuse with itself. But the main problem is that the fusion product is unstable. This is what I mentioned before. So we could fuse two helium-4 nuclei, but the result is beryllium-A, which is unstable. However, we can get around this if we're able to very quickly fuse the beryllium-A with another alpha particle or another helium nucleus. So this is what's called the triple alpha process, and by doing this we're able to convert 3 helium nuclei into carbon-12, which is stable. So this happens generally towards the end of a star's life. So after it's used up its core hydrogen, it will enter this stage. Now, many of the stars that we can see with our own eyes actually are already in this stage. So at this point, a star generally swells and increases in luminosity to become what we call a red giant or a red supergiant. Here is one example of a red supergiant. This is the star Betelgeuse, which, as you can maybe make out from the right-hand side image, is actually one of the stars in the constellation of Orion. Hopefully you can just about see the shape of Orion there. Now, Betelgeuse is really interesting in itself because over the last few months, Betelgeuse's luminosity has been changing very rapidly, and some astronomers were hoping that this was a precursor to Betelgeuse actually exploding. Okay, so low-mass stars unfortunately never fuse beyond carbon and nitrogen, and this includes the Sun. Instead, their core collapses to form an inert lump of material called a white dwarf, with the remaining material actually expelled to form this envelope of material around it called a planetary nebulae. So this is just a very simple schematic over here, how we take a star like the Sun, and towards the end of its lifetime we'll be left over with this small white dwarf, which is no longer creating energy via nuclear fusion, surrounded by this diffuse material called a planetary nebulae. Here is a white dwarf. It's not the main object in the centre of the screen, but it's this little dot down here. In fact, this main object is the star Sirius A, so one of the brightest stars in the sky. Sirius B down here is this little companion of Sirius. Planetary nebulae are these diffuse gas which surround these leftover remnants of stars like the Sun, and they all look different. So this is just a small collection of some of the planetary nebulae that we can observe in our own galaxy, and you can see there's lots of different structure in some of these different images. They are some of the most beautiful objects that we've discovered in the universe so far. Now, if we look at the contribution of these low-mass stars to the periodic table, it turns out these stars can produce large amounts of carbon and nitrogen, and also fill in the remaining lithium. But that's about it. So they don't do much else. Actually, that's not entirely true, because it turns out that low-mass stars can also produce some heavy elements, but to do this they first needed to be seeded with some existing heavy elements. I'll talk more about this in a minute. Now, in stars more massive than the Sun, the cores are eventually able to reach higher temperatures so we can progress beyond pure helium fusion. They do this by fusing the result of the previous reaction with another helium-4 nucleus. This is something called the alpha process or ladder. And to give you an idea what happens here, we can see this. So for example, we can take carbon-12 and we can fuse that with another helium-4 nucleus to form oxygen-16, and so on, all the way up here to iron and nickel. Okay. Now the interesting thing is, when we get to iron and nickel, actually fusing beyond there requires more energy put in than is actually released in the fusion reaction. Before this, every single time we made a heavier and heavier element, we were still getting energy out. And that's really important because fusion is the only way the star is producing energy to support itself against the collapse due to gravity. And so when we get to nickel, we suddenly run out of energy. Now it's worse than that because the process is endothermic beyond nickel. The star doesn't know to stop, and so it actually tries to fuse beyond nickel. But this saps the core of energy, meaning it no longer has any pressure to support itself, and it rapidly collapses underneath its own gravity in an explosion called a core collapse supernovae. Now these core collapse supernovae themselves are really important because they disperse all of the elements which have been forming in this star into space, where they can be locked up into a new generation of stars. Here's an example of a star which has exploded. These are the leftover remains. Now the material that you see here is enriched with heavy elements. So if we now add in to our diagram the exploding high mass stars, we see that we're really beginning to fill in large amounts of the upper part of the periodic table. Okay, so we can see that many of these bits are filled in now. We're even starting to get some of the iron. Okay, but so far I've talked about high mass stars and low mass stars, but we still haven't really explained all the periodic table. There were some notable gaps just in the bottom of the periodic table here, let alone the rest of the periodic table, the high mass end. Well, the solution to this is the fact that most stars actually exist in binary star systems, and in many cases in triple star systems. Now in some cases, two stars are close enough that they can interact. In one example of an interaction, a white dwarf can actually accrete material from its neighbour. As it gains material from its wider, bigger neighbour, the white dwarf gets denser and denser and denser. If this process continues, at some point the white dwarf is no longer able to support its weight and it suddenly collapses. And as it does, it heats up, and this triggers a huge thermonuclear explosion through which the white dwarf. We see these events as type 1a supernovae. This is a slightly different type of supernovae. So here's an example of a type 1a supernovae. What you're seeing here on the bottom left-hand corner is this single star, about the mass of the Sun, exploding. Now this produces the same amount of light almost as the entire galaxy which you can see above. This entire galaxy here contains hundreds of billions of stars. Again, these explosions leave this leftover material which can go on to form new generations of stars. So if we add in the exploding white dwarfs now, we now see that we're really doing a good job in actually explaining most of the upper part of the periodic table. Okay, but again, there are still some gaps. But let's just take away the white dwarfs where we can see the difference. What you can see here is that what the white dwarfs have added is mostly the iron series elements, so around iron and manganese and cobalt. Okay, but we're still missing things down here. Now, many of the nuclear reactions that we've described so far produce large numbers of neutrons. If we have large numbers of neutrons, these can be absorbed by nuclei to make successively heavier atoms. This is what we talked about right at the very beginning when we talked about neutron capture. So, in this example, we have on the y-axis the number of protons, so this tells us the periodic element, and on the bottom axis we have the number of neutrons. So silver 109 can be converted into silver 110 by capturing a neutron. But silver 110 is radioactive and it wants to decay via beta decay. Now in this context, what beta decay does is turn a neutron into a proton and an electron and an anti-neutrino as well. And so with beta decay, we actually convert silver 110 into a new periodic element, cadmium 110. Okay. Now if there's enough neutrons around, cadmium 110 can continue to absorb neutrons, and this whole process can continue. So via this process, we can create heavier and heavier nuclei. So as you see here, that cadmium 110 can capture neutrons to become 111, 112, 113, 114, 115, but 115 is again unstable and decays via beta decay to produce indium. And again, we can build up successively larger and heavier nuclei in this way. And so when we take our low mass stars and our high mass stars and our type 1a supernovae, okay, we can add in the contribution to building these heavier elements in. And we're now starting to populate the bottom half of our periodic table, so the very massive elements. But we can see there are two crucial gaps missing. There's this one here with beryllium and boron, and there is still obviously lots of the heaviest elements that we haven't yet explained, and this includes gold and platinum, the elements that we really care about. Well, to explain boron and beryllium, this is actually a little bit boring, but this is a process called cosmic ray spallation. Now, if you take a carbon-12 nucleus, which is fairly abundant in the solar system, and you strike it with a cosmic ray in this context is normally just a very high energy proton, that cosmic ray can actually knock off one of the protons in carbon-12, leaving boron-11. Now, if the boron-11 then gets hit by a cosmic ray as well, you can actually turn the boron-11 into beryllium. And so by adding in cosmic ray spallation here, we're able to explain now the boron and the beryllium. Okay? But we still haven't explained the bottom half of the periodic table down here. Now, the origin of these extra elements, which we haven't yet explained, lies in a new type of interaction. And this is a new type of interaction where neutron stars merge together. Now, I haven't introduced what neutron stars are yet, but they're the leftover remains of very massive stars. So when we have one of these core collapse supernovae, we don't always destroy the star. In many cases, we're left over with this incredibly dense remnant called a neutron star. It kind of is what it says on the tin. It's a star which is mostly composed of neutrons. Now, these things are incredibly dense. Now, occasionally, pairs of neutron stars can in-spiral and eventually collide. Now, when they do this, they're going to release huge amounts of neutrons, allowing heavy elements to be assembled through neutron capture and subsequent decays. While previously hypothesized, this was actually only confirmed relatively recently. In fact, the first neutron star collision was detected in 2017. And it was detected not in visible light, first of all, but actually using gravitational waves. Gravitational waves are radiation produced by masses as they spiral into each other. This is actually a very different way of looking at the universe compared to visible or even infrared, etc. light. Now, what was really great about this detection is that we were able to very quickly take our normal telescopes and look in the location of where this gravitational wave signal came from and actually look and see if we could see anything. And lo and behold, we saw this bright spot of light, like a little supernovae. Now, when we looked very carefully at this light, we saw the telltale signature of heavy elements actually being created here. And so when we add in neutron star mergers now, it turns out we can explain the entire periodic table, not just the abundances, okay, but the origin of all of these elements. Just to point out that there are still some elements that are not quite explained here. They don't exist in nature because they're all radioactive. So for example, technetium here, with a number of 43 between molybdenum and ruthenium, okay, that actually has no stable isotope. And although it does exist in trace amounts on the Earth, it's very transitory, so it's produced by the decay of other elements. Okay. So although we've now got to the position where we can explain the entire periodic table, it's worth just noting that astronomers currently believe that the entire contents of the periodic table only make up a small fraction of the energy content of the universe, with the rest being in dark matter and dark energy. Exactly what these are actually remains unclear, and this is where most of astrophysical research is concentrated these days, trying to explain what dark matter is, which appears to be a source of gravity, and then trying to explain dark energy, which is something even more mysterious, which appears to be driving an accelerated expansion of the universe. But that's perhaps a talk for another day. And so just to conclude here, the atoms that make up your body were mostly produced during the death throes of massive stars billions of years ago. However, the precious metal in your jewellery was mostly created when two neutron stars collided. Okay? Arguably, this is even more impressive than your jewellery being forged in the fires of Mount Doom. At least it's a much more energetic process. But just to end this with, we still don't have a good idea what 95% of the universe really is. So this is the dark matter and the dark energy. And just as a final advertisement, hopefully we'll have the Webb telescope coming next year, which will hopefully solve some of these additional mysteries and fill in the final details. And thank you for listening, and I hope you are able to enjoy many of the other Sussex Universe online talks.